Hi, my name is Murthy Upmaka. I'm a solutions engineer for Keysight Technologies. In this video, I will examine the noise correlation and its impact on phased array performance. Phased array antennas can potentially improve the signal to noise ratio, whereas single antennas cannot. This is perhaps the topmost reason for adopting array antennas in almost every wireless communication system. The SNR improvement is a result of non-correlative property of the noise present at its input. Is a noise always uncorrelated? Not necessarily. It could be both correlated and uncorrelated. By looking at the noise, we would not even know whether it is either of them or both of them. What happens if we have both correlated and uncorrelated noises present in the system? How does phased array perform? Let us examine all of the above with SystemVue. In this schematic, we have only correlated noise. We took a single oscillator and set up its signal power to be 0, whereas 0 watts, whereas the noise density set up to an arbitrary value, minus 154 dBm per hertz. Then we split that into equal 144 channels. We combined all 144 of them and monitored the spectrum at the output. We also monitored the spectrum at the input of the combiner, as well as we collected the samples into a numeric sink. If we notice the spectrum from left-hand side, which is the input, to the right-hand side, which is output, we can see that there is a amplification of the noise by about 20 dB. Very easily we can see that. This amplification of the noise indicates that the noise could be correlated. We can perform a simple test by collecting the samples in two individual channels and then performing a cross correlation between them using a script shown here and plotting it to notice that we got a distinct peak in the middle, indicative of the correlation property of the noise. Let us go and then examine in the case of uncorrelated noise present in the system. In here, instead of one oscillator, we took 144 individual oscillators. The thick arrow indicates a matrix. It's a matrix of 144 oscillators. Then we combined all of them and monitored the spectrum. We set up the power of the oscillator to be 10 dBm and the noise density to be at minus 150 dBm per hertz in each one of these oscillators. Now, if we see the signal to noise ratio from input to the output, at the input, we have a signal to noise ratio of 110 dB. At the output, we have a signal to noise ratio of 131.58 dB. So we have a clear improvement of 21.58 dB of signal to noise ratio. This improvement came about because all the noise was uncorrelated. The combiner could not add them up, whereas the combiner added the signals very effectively. What happens if we have both correlated and uncorrelated noise present in the system? Then we have to consider the relative levels of the correlated versus uncorrelated noise. Let us set up the correlated noise to be a very tiny value compared to the uncorrelated noise. If we look at the spectrum, we see that again, same thing. We notice about 21.58 dB improvement in signal to noise ratio. So we got the full advantage of the power combiner. If we change the relative levels of the noise contributions, we keep the correlated noise slightly below the uncorrelated noise so that we can still see some improvement in signal to noise ratio. We notice that the signal to noise ratio at the input is about minus 91, 92 dB, and at the output it's about 98, 99 dB of signal to noise ratio. So a clear improvement of about 6 to 7 dB from input to the output. So we did not get the full advantage of the combiner, but we did get some advantage of improvement of signal to noise ratio. This is what exactly happens in a phased array. Before we go on to the phased array, in most practical phased arrays, we use RF power splitters, high frequency power splitters. These could be typically Wilkinson power dividers. So this power splitter takes the noise at the input and divides equally to the output. While doing so, it incurs a loss of both insertion loss plus split loss of about 22.58. In this case, the insertion loss could be even much more in a practical power splitter. So at the output, the noise will be appearing in each one of these individual channels reduced by 22.58 dB. Because this is a passive component with loss, it will appear as if it has a noise figure of 22.58 at the IEEE room temperature. This will produce a noise equivalent to KTB-NF. So it will add its own noise contribution at the output into each one of the individual channels. This noise produced by the power splitter is non-correlative. It's uncorrelated. So in a practical power splitter, at the output, we will always see both correlated and uncorrelated noise. Let us go in and examine a phased array schematic where we have both correlated and uncorrelated noises present. The relative levels are set like before. We kept the correlated noise slightly below the uncorrelated noise. And we can steer the beam in any direction, monitor the spectrum in the far field radiated by this array antenna model. Now we see that again we get an improvement of signal to noise ratio from input to the output of only about 6 to 7 dB because both correlative and uncorrelative noise are present in the signal. So a phased array similar to the power combiner, in fact we call that as a beamformer in phased array systems, will give varying degrees of signal to noise ratio improvement based on the incoming contributions, incoming noise with contributions from correlated and uncorrelated portions. It should also be noted that as you steer the beam using the phase shifter, the gain of the array will vary. The gain of the array consists of two parts, array factor and element factor. The improvement of signal to noise ratio is entirely due to the array factor. It does not depend on the element factor. This also becomes a very nice tool in our hand. If we want to improve the signal to noise ratio, we could potentially increase the size of the array and get a better to signal quality at the output. I hope you enjoyed the video. Thank you very much for watching.